Looks like most of you also kind of finished the quiz. Again, there were a lot of questions, but again, it was more just to give you I guess a wide breadth of all the different kind of things that in future programming assignments we'll almost assume that you know those heading into the assignment. I can look into Connects issues. Again, I know some of you that have other midterms today are probably worried because you might have other Connects issues. At this point, I'd email your instructors of other courses you might have midterms in right away, just so they're aware of it. And David, who also might be more familiar with this issue, who's our senior lab instructor, saying that last time this happened, students using some ISPs were unable to resolve Connects due to DNS problems. But again, people like Omar are saying that this hasn't fixed their issue. Again, some of you are privately messaging me asking what to do for again, other midterms and stuff today. I'd email your instructor right away, just so they know beforehand that you're experiencing issues. Again, it's always easier to deal with beforehand as opposed to emailing them after you've missed the exam, and then there's a whole bunch of other issues that it complicates things. And again, someone I think asked, it might have been in my other lecture, asking whether or not any quizzes will be dropped at the end of the term. I mean, that's something that certainly I can look into. And again, if there was a whole bunch of Connects issues for people today, and some of you are maybe even saying other days, what I could do is just kind of drop one or two quizzes from everyone's score or something like that. So I guess, yeah, I guess so. Maybe not all of you can see what I'm seeing on Connects, but I guess hopefully some of you are able to go through some of these videos before losing Connects access. If not, I could maybe just try and send out a link to a lot of these videos, because they are all hosted and you don't necessarily have to access them through Connects. So we'll see. I'll look into the connection issues immediately after class, and if there are kind of issues preventing you from accessing Connects for a little bit longer term, I'll definitely make sure that everyone has access to these lecture videos, and I can send out links outside of Connects if need be. I guess for those of you that, it seems again that about 100 of you, which is kind of the highest number of people that usually access quizzes, were able to access the quiz. For those of you that and maybe kind of looking mostly towards those of you that took 111 or 116, those of you that maybe hadn't done a lot of Java programming before, what were the main issues that seemed new or different to you? Just so I'm aware moving forward. Because again, I'm more familiar with what concepts are taught in 110 and 115 as opposed to 111 and 116. So just not used to the general syntax. Yeah, okay. Yeah, I think, again, as I said, from a logic kind of, in terms of the logic with respect to these different loops and if statements and whatnot, it shouldn't be any different than what you saw. But I know, yeah, like even in the Python 110 course, previously when 110 was taught in Java, there was quite a lot of focus on arrays and two-dimensional arrays, whereas now instead of two-dimensional arrays, typically there's an assignment on dictionaries. So there are some things that might be new to you based on how even 110 has changed. And also, I'm not sure how, since I've come back to you, Vic, I'm not sure of the kind of details in terms of what's focused on it in the assignments in 111 and 116. Okay, that's good to hear, Natalie, that you mostly found it okay, but just some syntax stuff. Okay, so yeah, because today is kind of the turning point. We're going to continue working on a worksheet, but we are going to kind of start shifting our focus a little bit and introducing some I guess, programming exercises into the labs and assignments. And again, our midterm is coming up in just a couple of weeks. So I think it's June 9th. So again, pretty close. I'm not sure if there will be much, if any, programming on the first midterm, again, because the first midterm will mostly focus on again, this first month of the course, when we're doing a lot of our kind of discrete math and our proofs and our kind of runtime analysis. But certainly in the following exams, there will be probably some programming components as well. That's really weird, Omar, that if you spam the refresh button, it works. So I guess yeah, so my apologies for those of you that aren't able to access Connects. But again, for the worksheet, the questions we're working on, again, if you start just from the document that you probably would have downloaded last day, or even if you just from a fresh document, there's not kind of much to write in terms of the problem description. So we're going to be focusing on questions 5, 6, and 7. And again, there isn't a ton of question description to write. So hopefully you're not too far behind if you actually have to start this from scratch in an empty Word file or something like that. Yeah, this dot is confusing, and again, when you're this dot comes up when you're working with classes and objects, where when you've got an object and it's got its own data fields or attributes or instance variables, depending on maybe what they may have been called or introduced to. But again, if we've got like a student class that has a student ID and a GPA and a program that they're in, those fields, those instance variables are accessible through all the methods within that class. And I guess the problem is, again, they're kind of similar to global variables, but the thing is, you can still have methods that have parameters with those exact same names. So if there's I guess when you have a method in the student class where students again have a student ID, a GPA, and a program, and you have a method that takes something, a parameter, and it's called program. When you're using the variable program within that method, what should it correspond to? The field for that object or the parameter? And I guess what Java's done is they've said with this dot allows us to explicitly say, okay, I'm referring to the field here, whereas without this dot, it's to the locally defined variable, which is usually a parameter. So you can use this dot whenever you're working with instance variables or fields within an object, but you only need to do it when you're trying to differentiate between two things that have the same name. Does that make sense? Yeah, exactly, Joshua. Yeah. Yeah, so what Joshua said in the chat is that this is just like Python itself. I'm gonna move some of my chat stuff off my screen. Any other questions before we move into this stuff? And again, I can try to either make videos or explicitly kind of mention things that I think are going to be new to people that haven't used Java as we progress through the course. But I think, again, in terms of algorithms, when we're talking about, again, just loops and if statements, which is kind of going to be what we're going to be doing when we're doing our analysis of algorithms and thinking about different data structures and whatnot as we progress through the course, a lot of it is going to be, again, just using these loops and if statements, which are virtually the same across most languages. How large are the Java assignments? Joshua was asking. I believe, again, in terms of the assignments, how long they take, I feel like, I mean, and I'm not sure how you're finding assignment 1 versus assignment 2. I'm feeling, or my goal is to kind of make the assignments all about the same time commitment. So I think it'll certainly take a few hours, and maybe depending on how tricky the actual problem solving is, it might take kind of a day or two to think about the problem before coming up with a solution. Just like I know some of you, it took a day or two to kind of think about some of the problems in the first 2 assignments before kind of thinking about how to progress through solving them. But yeah, I don't think they're going to be like, again, I'm hoping that they're about the same size as the first 2 assignments. Does that make sense? I mean, obviously, some people are more comfortable and have a stronger, maybe discrete math background, so they might move through those faster. As some of you may have programmed. I have a lot of previous Java programming experience and maybe done a lot of the data structures and algorithms that we're focusing on in this course. So again, it's going to be different for everyone, but I think assuming the kind of prerequisites coming into this course are and that's kind of the experience people have, I'm trying to kind of balance it based on that. But yeah, there are certainly people that will maybe get through the programming assignments more quickly, for those of you that have a lot of previous experience. Any other questions? I'm going to start moving my tablet over here a bit. Okay, so what we're going to do now is solve a little o and a little omega problem, which again is when we're doing a strict upper and lower bound. And I guess it was now a couple days ago when you probably watched the I'm sorry. So for those of you that aren't watching the chat right now, Dave said that our IT is working on resolving the connectivity problem right now. So hopefully it'll be fixed soon. And those of you that, again, probably the biggest concern for most of you is if you've got an upcoming midterm on Connects, hopefully, at least if they're aware of it, hopefully those issues will be fixed as soon as possible. So yeah, in the video when I was talking about little o and little omega, I talked about the fact that we're going to prove that it's strictly less than or strictly greater to by using limits as n approaches infinity. So what the formula I outlined in the slides was we're going to do this, whereas this is going to be the running time of the algorithm we're looking at, and this is going to be what we're proving it's little o of. So what I can do here is I can rewrite this and say, okay, this is equal to the limit as n approaches infinity of n cubed plus 4 over n to the 4, which I can, again, just separate these terms out by saying that this is the limit as n approaches infinity of n over 3 over n to the 4 plus the limit of 4 over n to the 4, which if we think about these two terms separately, really we're just really we know that again, as I guess as this approaches infinity, this is going to approach 0, and as 4 over n4 approaches infinity, this is going to approach 0. Again, we could simplify this further if we need to, where we know 1 over n is just going to be 0 plus 0. And so because this, maybe I'll put it over here just so I can write a line below. And so again, by I guess the definition of little o, if as n approaches infinity, I guess one function over the other function approaches 0, then we say that it is little o of that function. So what we'd say here is therefore the function n cubed plus 4 is little o of n to the 4. And I'll ask for questions about this, but I just want to again say that David in chat just said that IT believes it has fixed the problem. Please try connecting to Connects again. That's, yeah, we'll use this I guess essentially this, when we're trying to prove something is little o. And if the limit as n approaches infinity approaches 0, then we'll say it's little o. If it approaches infinity, then we'll say it is little omega. I'm getting some reports that it's working now. So I guess the difference between this and what we'll do for the next one is the limit when n approaches infinity of t of n over fn. If it approaches, we want to show that approaches infinity for it to be little omega. But before I start the second one, I can just ask if there's any questions on how I did any of the steps in the first one. Looks like it's okay. So I will keep going. Again, so I'm just going to rewrite this and actually put in the functions of n cubed plus 4 over n squared. Again, I can separate these terms the same way I did before. So again, obviously the term here that makes this different is before in our previous one, we had limit of 1 over n as n approaches infinity. Now we've got the limit of n. And again, as n approaches infinity, obviously, so will n. So here we can say n cubed plus 4 is a little omega of n squared. Any questions about, I guess, the second, or I guess either of the two here? Okay, I'll leave it up here for another second, and then I will scroll down and we can work through our last problem. And then once we do that, I do want to kind of pull up an editor really quickly and do a little bit of programming. Oh, sorry, this should be 4. So this is 4. Good catch, Shen Yao. Again, all I did is I just divided both of these by n3. So if you divide both these by n3, this will go to 1 and this will go to n4. But yeah, I don't know why I got rid of the 4. I shouldn't have there. This should be a 4. And as Andy's saying, just looking at the degrees of certainly the end terms and just moving straight to the result, that's perfectly fine. I think I showed here more steps than I feel like are necessary or required if something like this showed up on your assignment. And again, maybe in your math classes, you're just going straight from this step right here all the way to the solution. Just by seeing that, n3 plus 4 over n4 as it approaches infinity is just going to be 0. Okay, yeah, good to know. So again, so Jacob's asking if for little o, shouldn't it be f of n is greater than Tn? So again, remember for big O, we're thinking about an upper bound. So we're saying that after a given point, this function has its upper bound is based on some other function, and typically n or n log n or n squared. With little o, we're saying that it's not just an upper bound. We're going to be strictly less than that other curve. So I guess the difference between big O and little o is little o is a stronger statement. Big O is saying it's less than or equal to, so it might actually be equal to that other curve. Little o, we're saying it's strictly less than this other curve. So we're saying that n cubed plus 4 is strictly less than n4 past some point. Does that make sense, Jacob? Okay, great. Any other questions before I clear this off and scroll down? So find a tight bound for a function that has a running time log n factorial. So in terms of big O, so I'm going to write this out. When I'm saying tight bound, we're talking we're gonna want to find both big O and big omega so hopefully we can find big theta, which is that tight bound. So first of all, we're going to need to think about big O, where if we've got T of n equals log n factorial, we're again going to have to refer back to our log and our log rules, and maybe also our what this means for factorial. And what this means is that this is just the same. I'll go down the line. This is the same as writing log of n times n minus 1 times n minus 2 times all the way down to 2 and 1, right? Just because that's what factorial is, from n, multiplying all numbers from n down to 1. But now for log rules, what this means is that this is equivalent to saying log n plus log n minus 1. Oh, sorry, I didn't write my n. Plus log n minus 1 plus log n minus 2 plus da 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 all the way to log 2 and log 1. So now, if we're thinking about an upper bound, we now see again that I've got n terms here, but I can say that all of these terms are going to be less than or equal to if I just set all these to n. Where here, what I've got is now I've got now what I've got here n terms. So I'm trying to sum together n log n terms. Which is just equal to n log n. So therefore, for our big O, we can say that this running time is O of n log n, with C and n naught equal to 1. So I guess before I move on, I'm going to do our big omega next. But before I do that, any questions about any of the parts I've done for big O here? Well, just because, again, there is no C is kind of right here. But this is just 1 n log n. And I guess this is going to be true for all n greater than or equal to 1. Because again, but if we're saying let's do log, if we're saying let's do log 3 plus log 2 plus log 1 or whatever, that's going to be, for all n greater than or equal to 1, that's going to be less than or equal to log 3 plus log 3 plus log 3, right? Just because, again, with big O, we always want to find, we're always looking for the, oh, I didn't know that was my eraser. We're always looking here for the upper bound. So we want to find something that is always greater than or equal to it for all n's past a given point. I guess it's similar to how with our other things when we had kind of some polynomial expression, we kind of said, okay, well, that's less than this. So I can say for all n past 1, this is going to be bigger than that because n cubed is going to go up faster than n and no n at all. So a tight bound just means that, again, because by definition, big O is just saying an upper bound. What I want is I want a tight bound. I want to see if I can classify the runtime of this without just saying, oh, it's way slower than this or way faster than this. A tight bound just means I want to say, oh, it's basically asymptotically equivalent to this runtime. Which what we're seeing is we're hoping now that since we found it was I guess a low bound on big O might be n log n. If we can, we're now hoping that n log n might be the tight bound, but we have to show that with big omega. So if we're saying it's at least greater than or it's less than or equal to n log n, I can show it's also greater than or equal to n log n, then we'll have a tight bound there. And we can say therefore it is this algorithm is going to be n log n. Does that make sense, Kevin? Okay, great. So now we want to do big omega. So again, we're going to start with the same thing. And we're going to expand it the same way. So I can say this is equal to log n, same thing as line 3 up here, plus log n minus 1 plus log n minus 2 plus and I guess so here what we're going to do here is if I've got is what I want to do now is say that I actually want to say that I want to write out another expression of terms, sum of terms. It's always going to be less than or equal to this. So again, if we've got n plus n minus 1, I'm just going to do a little sidebar over here. So if we've got n plus n minus 1 plus n minus 2 plus somewhere in the middle, we're going to have n over 2 plus n over 2 minus 1. So we're going to have like, if it's like 10, 9, 8, then we're going to have 5 and 4 kind of somewhere in the middle. Let me write this a little nicer. And then we can keep going, and we're going to have like 2 and 1, right? So again, I've kind of said it, I could have 100, then 99, then 98, then somewhere here in the middle, I'll have 50 and 49. And then I can keep going, and I can have 2 and 1. Yeah, and what Andy's saying, another way to solve this is just to bump up the C a bit. But another thing I can do is we know that all of these all the terms, kind of the first half of these terms, are all greater than or equal to n over 2. So these are all greater than or equal to n over 2. So if I set all of these first half terms to n over 2 here, so I'm making, instead of these n, I'm saying this is equal to n over 2, and this is n over 2, and this is n over 2. And I'm decreasing, obviously, n over 2 is going to be smaller than all these values here. If I do that, and then I say, oh, and also for the second half, I'm just going to make these, I'm just going to get rid of these. I'm just going to set them to 0. So what I've done is I've said, let's only now have the top half of the terms. Let's set those down to n over 2, and then let's get rid of the second half. So what I'd have here, I'd have, instead of having 100 all the way down to 50, I'd be summing the 50 elements from 100 down to 50. I'm summing the 50 elements. I'm just summing 50 n over 2 times. So what I can do here is, instead of, again, summing up the first n over 2 elements from log n down to log n over 2, I'm saying that if I only have the first half of these elements, n over 2 of these elements, and then I get rid of the second half, then that's definitely going to be less than or equal to log n plus log n minus 1 plus log n minus 2, et cetera, et cetera. And what I've got here, because what this equals is, this means I've got n over 2 log n over 2s. Which equals n over 2 log n from our log rules minus log 2. And again, my logs are base 2. And if I've ever got log 2 base 2, that just goes to 1. So this is equal to n over 2 of log n minus 1. And I can say n over 2 log n minus 1 is always less than or equal to n over 4 log n for all n greater than or equal to 4. So what we've got here is we've now said that this is big omega of, oh no. Therefore, we've got this is big omega of n log n with c equal to 1/4 and n equal to 4. Or should I write this? I can write this. Let's see. So I'll try and answer your questions. What I'll do is, I guess, for lack of space here, basically with for our big theta, our tight bound, I can kind of say 1 and 2 again, because with big theta, 1 and 2, if we're saying that something, by definition, something is big theta if it's O of n something, or big O of something, and a big omega of something. So what we've shown in 1 and 2 here, because of 1 and 2, we can say that T of n is also a big theta of n log n. I can, and then maybe I can, if there's a step in this that's confusing, I can, after we've got this down, I'll let people copy this down for a second. I can clear some space and draw over the proof a little bit if you'd like.
Howdy there, Papa.
Sonny boy, how are you?
I'm lovely. How are you?
I'm okay. I see that you was giving me a telephone call.
Well, I was wondering if you'd want to do some picking up here, as we will be returning to your house for the sushi.
Yes. Sorry, when you thinking about picking up?
I am done at 11:30.
So there's some questions, I think, here. I'll try to highlight it. I know some of you are probably still copying it down. Why n over 4 log n is less than or equal to n squared log n minus 1. So when
Hello?
that's only when n is greater than or equal to 4. So when n is 4,
I'm done at 11:30. Yeah.
they're
My challenge is having a barbecue.
when n is 4, we've got 4 over 2, which is 2 times log 4, which is 2 minus 1.
Ooh, yeah. And
So that's just going to be 2 is
I know
greater
I
than
could
4 over
do
4,
one
which is
time,
1.
but
And
then
then
I'd
from
have to
there
turn
on,
it
this
and then get up.
if we're dividing something by 4, it's gonna dominate dividing something by 2 and then subtracting 1 from it. So again, this is always gonna get smaller and smaller.
Okay. Sounds good.
Okay.
All right, great. Well, I'll be seeing you later.
Excellent. Okay. Talk to you soon.
Bye bye.
You don't know where the n over 2 came from. Yeah, so I guess this is when you've got, this is the way that I was taught this, and I saw in some of the different textbook descriptions it done this way as well. When you're doing kind of big omega, when you're trying to find something less than or equal to, and you've got a sum of n terms like we had over on the right here, you can kind of just say, okay, if I'm summing from 1 to n, summing just half of those terms at n over 2 is always going to be less than or equal to it, because we're getting rid of the lower half of the terms. We're saying those to 0, and 0 is obviously less than the sum of all these. And if we're setting the top half of the term, so all the numbers that are n over 2 or larger to just n over 2, we know that they're also always going to be less than or equal to the terms that we're not dividing by 2. And I guess for here, you could do it with, and this is something that Andy suggested, and maybe the way he did it is easier for some of you, is in that, again, this C term that I chose works with this n naught, but you can choose higher or lower C terms, and that'll affect when those curves change. And so when the point, I guess when the log, this log n factorial curve, based on what, when it I guess starts going higher than the n log n curve. If you chose n over 3, you'd have to solve for a different n naught. So 3 over 2, like the problem with choosing 3 is it makes the simplification much more difficult, because then you got a fraction here, 3 over 2, and log base 2 of 3 is also going to be a decimal that's going to be harder to solve. Putting in 4 just makes it a lot cleaner, because log 2 or log of 4, so log base 2 of 4 we know is 2, so that makes this thing in here 2 minus 1, which is really easy to solve to get your n naught. Yeah, Bryce, the big idea for the tight bound is you just want to show that asymptotically both the lower bound and the upper bound are the same. And then you've got a tight bound on what you know the running time of log n is going to be. We've been assuming that, unless otherwise specified for this course, that when we say log, we're assuming base 2. And that's just something for this course. But I mean, in general, I feel like most of the time when I'm doing any algorithm analysis in any course, or you're usually assuming log-based too. Any other questions? Okay, so I did want to maybe do a little bit of programming, but we can push that off to next week because our next unit actually focuses more on kind of programming and implementation. So maybe it makes more sense to push it until then. So again, there will be a little bit more review as we jump into some of our data structures, because I think in your prerequisite courses, you've probably seen and implemented things like a stack and a queue and a linked list. So again, those are going to be, I guess, data structures that we're going to talk about and review a little bit, and maybe focus a little bit more on the analysis of the speeds of the common operations associated with using these data structures. And then from that, we're going to start exploring other data structures and algorithms associated with those other data structures. And I guess really see why the new data structures we're going to learn are maybe better options in terms of our runtime analysis. I guess any questions on this before we stop the video for today?